Hi everybody. This video will cover section 4 of chapter 6, and in this section we are going to talk about the translations of the graphs of sine and cosine functions. Specifically, we're going to talk about the horizontal translations, the vertical translations, and the combinations of all possible translations, both horizontal and vertical, and also how they might apply to the stretching and shrinking relative to the amplitude in the period. Okay, so let's get started. Right here we have a graph of a basic function. This function really is nothing more than 1 minus the absolute value of x when x is defined between -1 and 1. Now, if I take this function and if I change the argument from x to x minus d, then what's going to happen here is that this function is going to transmit horizontally, as you can see. And if it turns out that if d is positive, like if d is equal to 3, then f of x minus 3 is going to be a translation of my base function to the right by 3 units. And then once again, if d is less than 0, then I will have f of x minus what's right there. I don't know why I'm doing it again. -3, which of course is just like f of x plus 3, which will be a translation to the left 3 units, or the absolute value d units, whatever d happens to be. Now, in circular functions, or namely in terms of sines and cosines, we tend to call this a phase shift. And it turns out that if the phase shift is equal to 1 period, well, the function really doesn't change because it basically translates 1 exact period and the function will look the same. But nonetheless, when we talk about this, we call this a phase shift. And ironically, we will call this a positive phase shift, and we would call this a negative phase shift. As would this be, since they're basically the same thing. Okay, so let's go ahead and look at an example. And here we are. Here we want to graph the sine of x plus 3 pi over 4 over 1 period. Now notice that we can write it like this. So we actually have the case where d is less than 0. So this is going to be a shift to the left. And what's one great way of looking at this? Well, here is sine of x. Okay, all we're going to do is take this function for 1 period, and we are going to shift it to the left by 3 pi over 4, and there we are. That's what we have it. That's where we have it. And that's pretty much the preferred way pretty much the preferred way to look at it from at least my perspective. Now, there is another way which the book discusses, and it's based upon the 5 important points of a sine function. And you know those occur when x is either equal to 0, pi over 2, pi, 3 pi over 2, and 2 pi. And remember, for those values, you would have that the sine of x would be equal to 0, 1, 0, -1, and then returning to 0. Now, since we have d is equal to -3 pi over 4, this is a shift to our important points. By how much? You guessed it, -3 pi over 4. So for our shifted function, our important points are going to be, well, not 0, but now 0 minus 3 pi over 4, or -3 pi over 4. And then the next important point will be pi over 2 higher, which would be -pi over 4. And then this one will be 3 pi over 4 less than that, or pi over 2 higher than this, and that would be positive pi over 4. This one would be 3 pi over 4. And you can once again find that by incrementing this by pi over 2, a quarter of a period, or just subtracting 3 pi over 4 from that. And then finally, we would have 5 pi over 4. And then, yeah, I know I'm running into this. Then the sine of x plus 3 pi over 4 at these values, again, would be 0, which is what you got there, 1, which you have here at -pi over 4, 0, which of course is what you have here at positive pi over 4, -1, which you have down here, and then finally 0 at 5 pi over 4. So those are the two ways to look at this if you actually need to plot it. Now, in your homework, you are not going to need to plot these things. Instead, not like this, because you're going to need to plot these using the sine and cosine tool that MML has to offer. And we're going to talk about this relative to this example right here. Here we need to graph y is equal to cosine x minus pi over 3. Now notice in this particular case, d is positive. D is equal to pi over 3. So the way to look at this is we're going to start with the cosine function. Okay, this is cosine of x. And then we're going to shift it to the right by pi over 3 units. And if you do, here's your function. Pretty straightforward. Of course, we need to be able to do this for your homework in MML. Okay, and this is the interface that we would use to do that. Now, how exactly will we do this? Well, it's kind of illustrated here. Or let's just go ahead and use the interface. So this is the equation that we want to graph. And the very first thing that you might want to do is come over to here, this graph right here, and basically zoom it up so it's a little bit bigger. That should work. And then come down here and notice here that you have a number of tools. You have the sine tool, you have the cosine tool, you have, I have no idea what that is, it's the region shedding tool, and that might come in handy, but you have to do inequalities. And then you have line styles and whatnot. Now, since we are dealing with the cosine function, we want to use the cosine tool, the one that's highlighted down here. So we're going to click on that, and then we can just click anywhere in the graph. And that is y is equal to cosine of x. Now we also have this dialog here, and we can use this to actually determine to make this equation fit, or to make our graph fit this equation. The first thing you want to do is check out the amplitude. Now notice here we are not scaled by anything, so the amplitude is going to be equal to 1, which is where it is right now. Okay. The period, once again, x is not scaled by anything, so the period will remain at 2 pi. 2 pi divided by 1, or 2 pi. There is no vertical shifting. We'll talk about that later in this video, so that will remain at 0. But now our phase shift is going to be positive pi over 3. Since this is x minus pi over 3, the negative pi over 3 implies a positive phase shift since we are shifting to the right. So our phase shift is going to be pi over 3, and you can put that in by typing in pi, that will make the pi symbol, slash, forward slash for the divided by, and then 3, and there you go. Now when you hit enter, you can see it shift. And if this was the and then if you would check your answer, and if this was the equation you're asking for, it would say that you're correct. Now in this particular problem, we're just going to go ahead and do this problem right here. They are asking for y is equal to cosine of pi divided by 12. Okay, and how would we do that? Well, I'm going to clear all this. Well, once again, you would make this as large as you want. It's large enough. Click the cosine tool anywhere, and then click anywhere on the graph. Here's a sine function, or cosine function, my apologies. Okay, well, the amplitude is still 1, the period is still 2 pi, there's no vertical shift, but notice here we have a negative pi over 12, so that is a positive phase shift of pi over 12. So backspace, pi divided by 1, 2, hit enter, and there is your phase shift. Not much of a phase shift because that's a pretty small number. That is 1/24 of a period, so that's not much at all. Okay, let's see if we're right. We can click on this to get our blue line, check our answer, and we are correct. So that's pretty much how you're going to do your plotting for a lot of for about 5 or 6 questions in MML. But we'll be going through all of the examples using MML as well, anyways, for the rest of the examples. So let's go on to the next example, and here it is. Here we want to graph y is equal to cosine negative 2 times the cosine of x minus pi over 3 over 1 period. And what I want you to notice is that this is the graph of negative 2, that should be an equal sign right there, I keep on forgetting to fix that, of y is equal to 2 cosine x, that is 1 reflected across the x-axis, and then shifted to the right by pi over 3 units because we have a positive phase shift. Okay, well here is the graph of 2 cosine x. Okay, here is the graph of, here it is reflected across the x-axis, which gives us the minus sign. Okay, and then here it is shifted to the right by pi over 3 units. Okay, so that's the way I want you to think about that. the base graph, well, the base graph actually would be y is equal to cosine x, which would start here and go down, scaling it up by 2. The negative sign, reflection across the x-axis, and then a negative pi over 3, positive phase shift of pi over 3. How would we do this in MML? Well, I'm glad you asked. Let's go to a similar question, not that it matters, because we're not going to plot that. We're going to plot this up here. Okay, so once again, make our graph big. Since we have cosine, click the cosine tool. Click anywhere on the graph. Our dialog comes up. Now, notice that since we have a -2, our amplitude is the absolute value of that, or it is 2. So we want to move this to 2. There we go. Okay, now, since it is a negative sign, we want to reflect this. Since there is a negative sign, we want to reflect this over the x-axis. There it is. Now there's no coefficient here, so the period is still 2 pi, and the phase shift is positive pi over 3. That's not a 2, 3, that's a 2. There we go. If we hit enter, there's our graph. And our graph should look a lot like the one period that we have here. Notice that it does. We are at -2 at pi over 3, just like right here. We go up to 1 at pi plus pi over 3, and then we head on back down. Because you can't see the rest of it because the range for this graph is not so big. So that is pretty much how you would graph this equation into the MML interface. Okay, let's look at the next example. Here it is. Now here we want to graph y is equal to 3/2 cosine 2x minus pi. But before we can graph it, we actually have to take this equation and we need to rewrite it so it looks like this. And what does that mean? Well, it basically means we need to factor out this 2 and then rewrite it and rewrite it in the form of 2 times x minus d, where d actually is the phase shift. We cannot determine the phase shift from this configuration. We need to factor out the 2 first. So let's go ahead and do that. And we will have that y is equal to 3/2 cosine 2 times the quantity x minus pi over 2. Now, are they equal? Well, 2 times x is 2x. 2 times negative pi over 2 is minus pi, so this works. Now, in this configuration, we can see that the amplitude is equal to 3/2. The period is equal to 2 pi over b, but b in this case is 2. That's 2 pi over 2, which is pi. And you can kind of see that right here. And now the phase shift is pi over 2. So I'm just going to call phase. I actually usually use a symbol for it, typically theta, but let's just use this for now. It's going to be equal to pi. Since we have a negative pi over 2, the phase shift will be positive pi over 2. Okay, and look what we have here. Here we have 3/2 cosine of x, and notice that the period is 2 pi. Here we have 3/2 cosine 2x, and notice that the period now is pi. Okay, which is what we expected. And then this is 3/2 cosine 2x minus pi, and notice that the phase shift here is pi over 2, and that's basically shift to half of a period. So once again, over here, this is equal to 3/2 cosine 2 times the quantity x minus pi over 2. So it's important that you rewrite this into this particular form so you can figure out the phase shift. Okay, now how will we do that in MML? Well, once again, we will basically make this a bit larger. We will click on the graph. And now, once again, since you're dealing with the cosine, we will pick the cosine tool. Okay, click on the graph again, and then we will go to work. Now notice here, let's bring this over here. The amplitude is 3/2, so we want to change this to 3/2 or 1.5. There it is. The period is pi, so we want to move this slider down to pi. Okay, and now the phase shift is pi over 2. So we want to change this to pi divided by 2. And also notice that this is positive, so there's no reflection across the x-axis. So we can hit enter, and that would be our graph. Now, do they look similar? Maybe we can do this. Oh, here we go. Well, notice here that when x is pi over 2, we have 1 here and we have 1 there. Great. When it goes down to pi, it comes all the way down to 0 like we would expect. Unfortunately, this graph doesn't do the rest of it, but you can see the rest of the cycle over here. And so they basically are the same graph. Let me bring this back down. Okay, so that's pretty much how we do that in MML. Now, the next thing that we need to talk about is vertical translations. And these, I believe, are pretty straightforward if you ignore the typos that I have in this slide. This should be a +3, not a +2. Now, once again, I have my little function here, f of x is actually equal to 1 minus the absolute value of x, but it's only defined when x is between -1 and 1. And why do I do that? Well, primarily because since it is bounded on the x-axis and bounded in the y-axis, we can actually see how it moves, both vertically and horizontally. Okay, and notice that if I add 3 to this function, it goes up 3 units. If I subtract 3 from this function, it goes down 3 units. And that's pretty much what we're saying here. If the graph of fy is equal to f of x, the entire thing plus c is basically translated vertically. If c is 0, if c is positive, it's c units up. If c is negative, it is the absolute value c units down, which is what you have here. And let's just play with this in an example, and let's use this one. Now notice here, we are going to graph y is equal to -2 minus 3 cosine 2x over 2 periods. So what do we have? We actually have a waveform whose amplitude is 3. It is reflected. Its period is going to be 2 pi divided by the coefficient next to the x, so its period is pi. There is no phase shift, but there is a vertical shift of -2. And here's what we have. Here is our base function, 3 times cosine 2x. Well, actually, the base function would be cosine 2x, but we're going to shift it up to 3. We're going to start here. I think it's a good starting point. Okay, then since we have a minus sign, we are going to reflect that over the x-axis. That gives us this right here. Okay, -3 cosine 2x. Okay, and then we're going to shift it 2 units down, which gives us this waveform right here. How would we do this in MML? Well, once again, here is our interface. Just raise the graph, zoom up the graph, pick the cosine tool again. I probably should have done more sine stuff. And there's our function. Okay, now our amplitude is 3. See, now, since we have all this bookkeeping here already, we can work with that. The amplitude is 3, so we'll just change this to a 3. We have a negative sign in front of the amplitude, so we are going to reflect across the x-axis to account for the negative sign. Okay, the period is pi, so we can just get rid of that 2 there. The vertical shift now is -2, so we are going to change this to -2. And there is no phase shift, so that stays the same. And if you'll notice, that this waveform and this waveform is pretty much the same. It starts at -5, just like we do here, goes up to 1, just like what we do here, and it continues in that particular fashion. So they are pretty much the same waveform. And if you click check answer, and that was the waveform they were asked for, it would tell you how absolutely brilliant you are. Okay, and this brings us to the last thing that we want to talk about, and that is, what if you have combinations of translations? Well, the key here is you want to work, if you actually had to graph this thing hand by hand, you want to account for the multiplicative transformations, and then the additive transformations, which are really the translations. Now, the multiplicative transformations basically are the amplitude, the period, and also whether there's a reflection. Probably should have had that in the slide. And of course, then the additive transformations, which are the translations, is the phase shift, or the horizontal shift, or the vertical shift, and the vertical shift. So do these first and do these next. Now, in terms of what you need to do in MML, what you need to do is what you need to do first is basically know what the amplitude is, know what the period is, know if there is a reflection or not across the x-axis. Okay, then you want to know what the vertical transformation is, and then we want to know what the phase shift is. You basically want to quantify these things and then fill out that little dialogue, and you are good to go. And let's do that in our, yes, you guessed it, our final example. So here we want to graph the equation y is equal to 4 minus 2 times the sine of 3 pi over x. Okay, check this out. We're actually doing a sine function this time. Well, first we want to write it in this particular form. And that really involves factoring out that 3. So when we factor out that 3, we're going to have 4 minus 2 is sine, which is perfectly fine. But then we're going to have 3 times the quantity x minus pi over 3. So in this case, we have that the amplitude is equal to 2. The period is going to be 2 pi divided by b, which is 3. So it's just simply going to be 2 pi over 3. And our phase shift, since it's a minus pi over 3, will be positive pi over 3, which, by the way, is 1/2 of a period. Okay, so let me write that stuff down just to make sure we keep it here, because we're going to need it in just a second. So the amplitude is 2. Should have done that the other way. We are going to reflect across the x-axis. The period was 2 pi over 3. We have a vertical shift of 4. And then we have a phase shift of pi over 3. And that's a positive phase shift. Now, if you were going to plot this, we would start off with, this would be our base function. Of course, with obviously the amplitude and the period is already incorporating this. So here's our base function. And notice that one period, that is 2 pi over 3 right there, so that's one period. This is the reflection of that base function, so that's negative 2 times the sine of 3x. This, and then this is the function shifted up by 4, and then shifted to the right by pi over 3. That point right there is pi over 3. So this is the function. This is what the function will look like for exactly 2 periods. Now in MML, how would you handle this? Well, once again, here is our graph. We can make this big by using the zoom symbol. Now you click on this, but this will basically give you a larger graph. You cannot affect the size any more than that. So I tend to like to use this because here I can make it as big as I want. I can sometimes even make it too big, like what I just did right there. Let me bring it back down. There we go. We can work with that since we're going to be going up in this direction anyways. Okay, so notice here we have sine, so I'm going to click on the sine tool this time, and then anywhere in the graph, there's my base sine function. My amplitude is 2, so I'm going to put a 2 in here. I am reflecting across the x-axis, so I'm going to click this. Okay, my period is 2 pi divided by 3. Now I already have my 2 pi there, so I'm just going to do my slash 3. There's my period. Okay, my vertical shift is 4, so I'm going to put a 4 in here. There's my vertical shift. And now my phase shift is pi over 3. So over here, I'm going to type in pi for pi, divided by 3. And there it is. And notice that these two graphs look pretty much the same. Here's 4. That actually is pi over 3. It goes all the way down to 2, which we have down here as well. It goes all the way up to 6 here. And then it crosses 4 at pi. And I cross 4 at pi, so they are the same. They are the same graph, although mine runs for 2 periods, and the graph in MML goes along forever. And of course, if that was the question being asked, and if you, whoop, didn't want to do that. And if you click this to make the line blue, and then Didn't want to do that either. And then checked your answer. If that was the question, then you would be good to go. And that is all I have for this particular video. If you have any questions, please feel free to contact me. This is Bob Boyle, signing off.